Chapter 2, Part 3, the Carbonyl Group and carbonyl-containing functional groups, and also nitriles. So, the carbonyl group is not really a functional group on its own. It's part of many functional groups. And since functional groups tend to tell you how something is going to react, you can't really group all of the carbonyl groups together because depending on what functional group the carbonyl group is part of, the chemistry can be very different. So carbonyl is often used like an adjective. The carbon of a carbonyl is sp2 hybridized. So this is a carbonyl. It's a carbon-oxygen double bond. So what I mean by carbonyl is often used like an adjective is that you can say this is the carbonyl oxygen, this is the carbonyl pi bond, and this is the carbonyl carbon. So it's a way of describing a piece of a molecule and not necessarily a functional group. So let's look at one of the carbonyl-containing functional groups, the aldehyde. For a functional group to be an aldehyde, the carbonyl carbon must have at least one hydrogen atom attached to it. The general formula for an aldehyde is RCHO, where the CHO represents the aldehyde functional group. You can also have HCHO. This is a very specific compound called formaldehyde. So an aldehyde looks like this. You have an R group, could be any number of carbons, maybe even that other piece contains other functional groups, but it's this part here that makes this an aldehyde. This is formaldehyde. The R group is replaced with a hydrogen, so this is the smallest possible aldehyde. This is benzaldehyde, which has the aldehyde functional group directly attached to a benzene ring. Also, fun fact about benzaldehyde, it smells like cherries and it can be found in almonds. This is acetaldehyde. It's a 2-carbon aldehyde. And this is the common name for it. The IUPAC name would be ethanal. This compound is vanillin, and just like it sounds like, it is a component of vanilla. And this last one is trans-cinnamaldehyde, and this one can be found in cinnamon. So looking at vanillin just for a second, vanillin is really interesting. It has 3 different functional groups happening, 4 if you want to count the benzene ring as a functional group. So we have the aldehyde, we have an ether, and we have an alcohol, which is more specifically a phenol because it is directly on a benzene ring. Now, ketones are very similar to aldehydes. The carbonyl carbon has to have 2 alkyl groups attached to it. The general formula for a ketone is RCOR or RCOR prime. So for example, you have your carbonyl, and on either side you have an alkyl group. It just has to be carbons, cannot be a hydrogen or another heteroatom. Has to be carbons. So this is the smallest possible ketone. This is acetone. This is cyclohexanone. This is carvone. This is a molecule that's found in nature. It's found in spearmint oil. This is 2-hexanone. Our next functional group kind of starts off another class of functional groups. So carboxylic acids are on their own a functional group. This is when you have a hydroxyl group attached to the carbonyl carbon. The general formula is RCOOH or RCO2H. So you have your R group, you have your carbonyl, and then you have a hydroxyl group attached to the carbonyl carbon. This molecule here is acetic acid. This is formic acid. This is benzoic acid. And then this is what a carboxylic acid would look like as a substituent. So the carboxylic acid could be sticking off of any other molecule. So talking about this, this, this. And when the carboxylic acid is a functional group, it's called a carboxyl group. You can also deprotonate a carboxylic acid pretty easily because they are in fact acidic, though they are weak acids. So the conjugate bases of carboxylic acids are called carboxylates, and their names of their conjugate bases match that. So you have acetic acid, when it's deprotonated, is acetate. And the substituent of a carboxylate group is just called a carboxylate group. Our next functional group are the esters, which kicks off our subgroup of functional groups called carboxylic acid derivatives. You'll learn about this more in OChem 2, but they're called carboxylic acid derivatives because they can be synthesized from carboxylic acids and can be hydrolyzed back to a carboxylic acid. So this is just a class of compounds, and they all have very similar chemistry. So esters is when you have an alkoxy group attached to the carbonyl carbon. We'll talk about what this means in just one second. The general formula for an ester is RCO2R or RCO2R prime. Most esters have a fruity or floral smell, so they are often used in artificial flavorings, and some are naturally occurring. So here is your general formula for an ester. An alkoxy group is when you have an oxygen attached to an alkyl group. So we have hydroxy that we saw previously. If you replace the hydrogen with an alkyl group, it becomes an alkoxy group rather than hydroxy. And when you have an alkoxy group directly attached to the carbonyl carbon, you have an ester. So for example, this is pentyl butanoate, and we'll learn how to name all these things later. Here we have ethyl acetate. This is a very common compound that you've probably interacted with plenty of times. And this one is isoamyl acetate. Pentyl butanoate has a smell like apricots and pears. Ethyl acetate is one of the ingredients in nail polish remover, and it has kind of a pineapple-y smell once you can get past the nail polish remover smell. And isoamyl acetate is really cool because it smells like banana runts, the little banana-shaped candies, and is commonly used as banana flavoring. Our next carboxylic acid derivative are the amides, and it's important to note that when you say amide, the I is a short I sound. There is another type of compound called amides, which is unfortunately spelled exactly the same way but pronounced differently. So the pronunciation does matter. And an amide is an amine attached to the carbonyl carbon. The general formula for an amide is RCO2NH2 for a non-substituted amide. A fun fact about amides: if you've ever taken a biochemistry class, you've heard about peptide bonds, which are the bonds that form between amino acids and build our proteins. Peptide bonds are just amides. So here is a basic amide. We have our carbonyl group, and then we have an amine, and you can substitute out these hydrogens for alkyl groups. It would still be an amide. The only important thing for something to be an amide is this bit right here, is that you have a carbonyl with the nitrogen attached. And again, the R group doesn't matter. It could be any number of carbons, could even be a hydrogen. So for example, we can have another substitution on the nitrogen. That would be called an N-substituted amide. You can have two substitutions on the amide nitrogen, and it would be called an N-N disubstituted amide. And here is a protein. This is a collection of amino acids here. And you can see that scattered throughout the protein, you have amide linkages. These are your peptide bonds. And these are formed through reaction between the carboxylic acid side of a amino acid and the amine side of an amino acid. So the word amino acid actually gives you a pretty good hint that an amino acid contains both a carboxylic acid and a nitrogen. So our last carboxylic acid derivative is the nitrile, and nitriles don't really look like a carboxylic acid derivative at all. The general formula for a nitrile is RCN. Carbon is sp hybridized. And what it looks like is you just have the R group, which could be carbons or hydrogen, and then you have the nitrile group, which is carbon and nitrogen with a triple bond. So it can be a really simple molecule, such as this one, where you have two carbons and then you have the nitrile group. This is ethane nitrile, or more commonly known as acetonitrile. And I've drawn this both as the Lewis structure and as the line bond structure, because when students are first learning line bond structures, they often lose the carbon here and assume that there's only one carbon in the compound. So you'll see this one, but students lose this one. This compound is propene nitrile, or more commonly known as acrylonitrile. This is a common monomer used in polymer synthesis. This is benzene carbonitrile, also known as benzonitrile. And this is cyclohexane carbonitrile and butane nitrile. Something interesting to notice in the nitrile is that just like with the alkyne, all of the atoms that are attached to the atoms within the triple bond are also in the linear form. So our geometry through here is linear. And so this is the appropriate way to draw out butane nitrile, rather than doing this and having your fourth carbon and then trying to stick off the nitrile off the fourth carbon at some like jaunty angle.